Well, let's do some substitution with some bounds in it too, huh? Got to get that practice, and that'll be it. Off to our first. What are we thinking here? What do you want? Let's keep it mellow. We don't want to get too crazy right off the bat. Go from 0 to 4 of x over the square root of x squared plus 9. Now, there's some textbooks that are just assholes, and they'll write it like this. I hate that shit. And you might find it. I'm actually looking at a textbook and taking it out of there, and they write it like that. F that. I always pull this dx to the outside, just so I can think of it. It's just a freaking placeholder. It's that thing I gotta match a game. So here it is. We have to do a substitution. I told you, look in denominators, look underneath roots, and take them constants with you. A perfect substitution here is going to be u is equal to x squared plus 9. Because when we take a derivative, it'll be, what is that? We're going to get du is equal to 2x dx. We lost a power. We lost a power, so we can match that thing up. It's very similar to the problem we did before. Now, if we're trying to make it to where this is going to match, we need to bring that 2 over, and we have 1/2 du is equal to x dx. Well, here's our x dx, so we're good to go. Let's roll. So we can say that this is equal, and I'm not going to write my bounds, because this is what it is all about now. So underneath that square root, we decided to call it u, right? And then instead of our x dx, we're going to write in 1/2 du. But again, I told you, I think that's silly to write the 1/2 up in the top. That's crazy. Let's put the 1/2 out front and just call it 1 over the square root of u. Well, you're going to have to deal with those bounds now, or you're going to have to deal with those bounds later. So here's your options. Change them now, and here's how it goes. The 4. When that's in terms of x's, we got to figure out what u is. So what happens when you plug 4 in for u? So we go, all right, when x equals 4, u is equal to 4 squared plus 9. U is equal to 16 plus 9. U is equal to 25. Boom. So we just converted x equaling 4 into u equaling 25. So we changed that. Now we got to do the same thing with 0. And we're just using this here. When x equals 0, u is going to equal 0 squared plus 9. Therefore, u is going to equal 9. So we'll take that 9 and we pop it on over into our new bounds. Now we're done. Now we never have to go back to x's again. We can just solve it. We put it into a better way for us to integrate. Call this u to the negative 1/2 power, right? That's going to be how we like to deal with powers. So let's go. Let's take its antiderivative. So we're going to add 1 to negative 1/2. That's going to become positive 1/2. And now we want to multiply by its reciprocal, which is 2. So there's that antiderivative. And now we can write in, we're going from 9 up to 25. We're plugging in our bounds. But we had to change them, excuse me, before we went in. So we cancel those 2's out. This is telling us that we just have the square root of u going from 9 up to 25. So we get the square root of 25 minus the square root of 9, which is equal to 5 minus 3, which is equal to a deuce. You get a 2. And that's what we call a fairly simple one when it comes to plugging in. Now, if you're someone that does not like that method, I will show you a quicker, or not a quicker, another way of doing it. So if we say we're going from 0 to 4 to x squared root of x squared plus 9, I'm just going to do this fast. And you're like, I don't want to change anything. I don't want to change anything. I want to just go to this point and I want to solve it. Well, you either need to stop writing your bounds in there, or you need to write it this way. X equals 4. X equals 0. Run through go get your answer that you get the 1/2 times 2 used to the 1/2 evaluated from x equals 0 into x equals 25. Then after you cancel this stuff out, you're going to get your square root of u evaluated from x is equal to 0 to x is equal to 25. Or shit, where am I writing? Those are the wrong numbers. Not 25 and 0. Those should be 4 and 0. I don't know why I'm writing that. Why did I change this to 25? I probably looked over and saw something. It doesn't change. The x is still freaking equal to 4. And then you would have to sub back in. You'd be like, no, this is the square root of x squared plus 9 evaluated from. Now you can write it from 0 to 4. And look what you end up having to do. You have to plug it back in. So you're like, all right, so it's 4 squared plus 9 minus the square root of 0 squared plus 9. That's the substitution you did back here. A lot of students want to get away from it. I know I did, and I did it this way all the time. I didn't realize I was actually doing more work. Oops. And you end up with 2. So there's your substitution. There's a method. This is typically when people think that they can like get around the system and like do less work. It's not less work. It's not. You end up having to do it no matter what. Okay. Gonna give you a tricky one and then we're out. I'm done. No more freaking videos for y'all. I'm over it. Let's do this beast. We're gonna go from 0 to 1/2 of 1 over 4x squared plus 1 dx. Now this is a level 7. This is a tricky one. This is, if you were in class, this might be a little more than I would want to give you, unless I just harped on it and done a lot of these problems. There is a weird ass substitution in here. And we have to create it with the idea of algebra first. There's nothing up here. I can't take that 4x squared and find a derivative. If I do it, u equals 4x squared plus 1, and I try and do that, I'm going to end up with du is equal to 8x dx. And there's no other freaking x's in here for me to cancel out. So this method failed. Shit. The only thing we could take a derivative on would be something linear, like a 2x or a 2x. If we draw this in just a tad bit differently, I think we could find it that we could write 4x squared as 2x all squared plus 1. This one is uber tricky. So now we can say, let's let u just equal 2x. And then du is just going to equal 2 dx. Let's divide the 2 over and we get 1/2 du is equal to dx. So we'll replace that dx with the 1/2 du. And we'll replace that 2x with a u. So what do we end up with? 1 over something squared plus 1. That's going to be a u. du, and there's that 1/2, huh? But we don't want to leave that 1/2 there. We want to take that 1/2 and put it out front. But oh shoot, we better get our bounds. We better change our bounds. But can you see the antiderivative there? 1 over something squared plus 1. Inverse tangent. We found it. And so there's a little inverse tangent trick. Be pros with inverse tangent. Your teachers, we love that shit. So when x is equal to 1/2, u is equal to 2 times 1/2. So u is equal to 1. So we replace that 1/2 with a 1. And when x is equal to 0, u is equal to 2 times 0, which is equal to 0. So that bound stays the same. We never have to go back to x's ever again. We're done with x's. We're now using u's. Plug your bounds in at the frickin' beginning. Don't wait to the end. That's my advice. Take it or leave it, though. You might watch a website, they're teaching you a way, and it seems to work better, so you go right ahead if you'd like to. That's just what I think. So the antiderivative of 1 over u squared plus 1 is inverse tangent of u. Now, since we have bounds, we don't write plus c. We write from 0 to 1. And we can say we have 1/2 inverse tangent of 1 minus 1/2 inverse tangent of 0. And I could have factored out that 1/2. Didn't have to do it this way. So this is 1/2 times pi over 4 minus 1/2 times 0. That goes away. And just leaves us with our answer, pi over 8. Substitution, dude. That's it. No more. I'm over.